Hello everybody, I'm going to talk about the normal distribution and the graphics display calculator. Basically, working with the normal distribution in its original function form ends up being some pretty tedious mathematics, so it's been simplified thanks to technology, and we don't have to use tables like we did in the old days, or we also don't have to use integrals like we did in the old days. So just a little bit of background, this function right here looks crazy. Of course, it's elegant because it has a square root, it has pi, it has e, sigma, and mu. It's a beautiful mathy looking equation. But at its core, it's really just a variation of an exponential curve. If you take e to a negative variable squared, you're going to get a bell curve shape. But the actual normal distribution itself, based on the mean and the standard deviation, is created by this particular function. So, if I were to graph this function, supposing that we go with the IQ standard, where the mean is 100 and the standard deviation is 10, then I'm going to see a curve that's going to bell out and maximize at 100, and then at 90 and 110, I'm going to see inflection points. It's one of the most elegant things about the normal distribution is that the standard deviation will always be at the first the inflection points will always be one standard deviation above and below the mean. So if you use this function here, whatever your standard deviation was, that's going to give you the inflection point of the bell curve. Anyway, suppose I wanted to know the area between the two standard deviations from the mean. All I'd have to do is integrate from 90 to 100. Oops, there's a typo. That should have been to 110. 90 to 110 of the function where I put in 10 for sigma, square it, multiply by 2, that's where I get the 200 pi. We're going to take e to the negative x minus 100, that's the mean, squared, all over 200, which is 2 times the standard deviation squared, dx. Again, this is not a fun integral just because of the squared variable in the e to the x. It's doable, but we don't have to. What we can do is go to the calculator. So you can see here, I actually entered in the given equation, this one, with the specific values for sigma and mu already. So I put in the entirety of that equation. And you can see that if I were to graph it, and here, let me clear this too, because we'll get to that in a second. If I was to graph this function, first I would need a good window. You notice my window goes from 70 to 130 because I'm trying to center it around 100, which is the mean, and I'm going up 3 standard deviations in either direction to see the curve. For the y values, we're not getting much because remember, we're talking about under the curve has to be a 100% probability, which means in order to get a 1 under the curve, you're going to have very, very small y values. And you can imagine that these are going to produce very, very small y values if you tried putting in numbers for x and see what happens. So that's why I made the y max 0.1, the y minimum negative 0.05. Now when I hit graph, you can see the bell curve. And then I could use my calculator functions. I go to second trace to get calculate options. And I can calculate the integral, option number 7, from 90 to 110. Hit enter, and it shades the area so I can see which portion of the graph I'm talking about, and does in fact produce a number value. So we have a 68.2% chance of falling 1 standard deviation above or below the mean in this distribution, and in every distribution. We'll always have a 68% chance of being 1 standard deviation above or below the mean. So that's the conclusion. Now, the problem is typing in this entire function every time you want to figure out the value of a normal distribution would definitely be time-consuming, even with this technology, which is why we've developed a distribution to get all of this information in one keystroke, if you will. So here's the trick. You in y equals, you can go to distributions, which is the second variables option right here. And right away, there's the normal probability distribution function, not the cumulative, but the probability distribution function. And when I hit enter, It asks for the x value. I want the x value to be x, so it's a variable because I'm in function mode. The mean should be 100 and the standard deviation 10, and when I hit paste, it smacks the whole probability distribution function right there for us. Now you'll notice I unhighlighted the original function that I typed in, and I highlighted the second function instead, and when I hit graph, I get the same curve as I did before. And just to test it, we can find the integral from 90 to 110, just like we did before, and it produces the same number value. So much easier, but we can even do one better than that. All we have to do is reset our calculator back to its normal calculator mode. Then we can go to distribution again, but this time I'm going to choose option 2, the cumulative distribution function. So basically that's going to not only present the function, but it will also automatically calculate the area under the curve from a left bound to a right bound. I'll show you. As soon as I hit this, the calculator is going to prompt me for the lower bound. In this case I chose 90, upper bound 110, mean of 100, standard deviation of 10, and then I hit paste. On the older calculators, you would have to type in these parameters: lower bound, upper bound, mean, standard deviation, and as soon as I hit enter, boom, it produces the same number, 68.2689%, just like before. So when you're using the cumulative distribution function, you don't even need to use the graph function in the calculator, and you don't even need to use the integral function in the calculator. It's going to straighten it all out for you. Now, one last question I would like to address would be, what if we wanted to find the probability using the same mean and standard deviation, mean of 100, standard deviation of 10. I just like those numbers. But what if I wanted the probability of x being less than or equal to 110? Now, first of all, when dealing with continuous variables, I can put less than or equal to. It's a horse apiece because we're dealing with integrals here. We have an infinitely narrow partition. But anyway, to get the area less than 110 requires a little bit of a game on the calculator's part, and it goes like this. You're going to go into your normal cumulative distribution function, so you go distribution, choose option 2 again, but this time instead of the lower bound being 90, we need a way to say negative infinity, and the calculator of course doesn't have a negative infinity, so here's how you do it. You type the number 1, and then here's how you get scientific notation. You use the EE, which is right above the comma, above the 7. So I do second, comma, and that's going to give me the scientific notation prompt, and I'm going to use negative 99. So if you don't know, that's how the computer was going to interpret specifically 1 times 10 to the negative 99 power. If you have an imagination, 1 times 10 to the negative 99 power is going to be, oops, I screwed up. We want this to be negative infinity, so I'm going to make that positive. Delete. I talked myself out of my own instructions here. And then I'm going to make the 1 be a negative number. Insert negative. So what I wanted, I just gave you 0 instead of negative infinity. This is a way to say negative infinity in the calculator. You take negative 1, and then you multiply it by 10 to the 99th power. There's your imagination for you. 10 to the 99th power is huge, times negative 1 is a huge negative number, which is, for the calculator's purposes, good enough to be negative infinity. The upper bound is still 110. Mean and standard deviation remain the same, and now when I paste this and hit enter, it is now producing 84%, which is basically going back to that bell curve we had before. That would be the equivalent of finding the area under the curve all the way to negative infinity, even though it's not practical. So I hope you found this helpful. Thanks for watching. Have a great day.